Okay, let's start the class. Okay, so this is the correction about the definition of subgraph. Okay, so actually, you don't need, so we say H is a subgraph of G if the set of vertices of H is a subset of the set of vertices in G, and also the set of edges is also a subset of the edges of G. Is that okay? So we don't need to have this vertex set to be the same as the vertex set in both graphs. So let's have an example. So let's call it G. This is the graph G. It is a very complicated graph. So if you look at this one, this is a smaller graph. So if you check on the vertices A, D, E, F, then we find that the edge AE is there, the edge AD is there, the edge ED is there, the edge EF is also there. Is that okay? So this is a subgraph of G. And moreover, this is an induced subgraph of G. Is that okay? Now, if you look at this one, this is a smaller graph. You just have AED. You find that the edge AE is here. The edge ED is also here in G. So every edge in this graph appears in G. Is that okay? So this is a subgraph of G. But on the other hand, this is not an induced subgraph because the edge AD is missing. So it is a subgraph, but it is not an induced subgraph. Okay? And finally, if you look at this graph, you have AE. You have AF here, but you don't have AF here. Is that okay? Now this is a problem. So this is not even a subgraph of G. Okay, so this is the definition. Okay. Okay, okay, now let us take a look at some example about the concept of isomorphism. Okay, so to show two graphs. Okay, so suppose that we want to show two graphs, G and H are isomorphic. They are isomorphic. What should we do? What should we do? If I have two graphs and I want to show that they are isomorphic, what should we do? So I have a graph like this. So the lollipop graph, and then another graph. And they have labels A, B, C, D, and then 1, 2, 3, 4, something like this. Then what should we do? So we have a graph G and a graph H. Then what should we do? Simple. We find the one-to-one correspondence. Is that okay? So just give a one-to-one correspondence is okay. So maybe in this case, let's map A to 3. Let's map B as C to 4. Let's map B to 1. And let's map A to 2. So you define a one-to-one correspondence, and then you ask the reader, you ask whatever, you ask our tutors to check that it is indeed a correct correspondence. So that you have an edge AC, and then you will then have an edge 3, 4. You have an edge CB, you will then have an edge 4, 1 in the graph, if and only if. So if this is the case, then this is isomorphic. Okay? Now, how about we want to show not isomorphic? Not isomorphic. So in that case, we will, one method, of course, the most naive method is you generate all the possible one-to-one correspondence, and then you argue that none of them is correct. So in that case, it is not isomorphic. But sometimes we can look at the graph properties and then argue that they cannot be isomorphic. So for instance, I have a graph G that looks like this. So And then I have a graph H that looks like this. Yeah, we have two graphs. They have the same set of vertices, but you can say that they cannot be isomorphic. Why? Why? There are many different ways to show that, but if they are isomorphic, they should have the same graph properties. So in that case, if you look at G, it has only one connected component. Everything is connected. G is a connected graph. H is a disconnected graph. So a connected graph and a disconnected graph cannot be isomorphic. Does that make sense? Okay, good. So let's see some example and see if we can get good reasons why they are not isomorphic. So I have two graphs here. Another example, let's say I have a graph here. So this is one graph, and then this is another graph. Okay. Okay. So this is a graph G, and this is a graph H. They may be the same, or they may be not. But first of all, let's check. Okay, let's check the vertices. Are they having the same number of vertices? If they do not have the same number of vertices, then they can't be isomorphic, right? So let's count. So it has 1, 2, 3, 4, 5, 6, 6 vertices. And here 1, 2, 3, 4, 5, 6, 6 vertices. Okay, so vertex has no problem. How about edges? Number of edges. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 edges. 1, 2, 3, 4, 5, 6, 7, 8, 9. So they have the same number of edges as well. But is there any way that we can, is there any simple observation that we can argue that they cannot be isomorphic? Number of what? Number of vertices, they have the same. Both of them has 6 vertices. Name. Well, now, if you check whether they are isomorphic, actually the name doesn't matter. So you can have the name here. Let's say A, B, C, D, E, F. You can have 1, 2, 3, 4, 5, 6. The name doesn't matter. Yeah, because we still need to find a one-to-one correspondence between the vertices. Is that okay? So to check for isomorphic, we actually look at the shape rather than the labels. Okay, the label is used to show that they are isomorphic, because we need to talk about the one-to-one correspondence. But is there any other properties about a graph that we can use to see? Okay, so what are the properties of a graph? Okay, so vertices is a property, number of vertices, number of edges. What do we know about graphs? Degree. Okay, excellent. Let's check degree. Okay, so what are the degree of these vertices? So this is a 2, this is a 3, this is 4, this is 3, 4, 2. Is that okay? Degree. And how about this one? This is 2, 2, 2, 4, 4, 4, right? Now you can see that the degree, they do not match. The degree set, the multiset of degree. So here, just take a look of this graph. It has 3 vertices of degree, on H, there are 3 vertices with degree 2. Is that okay? Now if they are isomorphic, then G should have 3 vertices of degree 2. Am I correct? Because it is going to be a mapping between vertices from one side to the other side. If there is a vertex of degree 2 here, you must find a vertex of degree 2 on the other side to map with it. Is that okay? So excellent. This is a good concept. So here we have 3 degree 2 vertices, and here we have just 2 degree 2 vertices, and they cannot be isomorphic. Very good, very good. This is a very clear proof that they are not isomorphic. Okay, so in that case, how about this one? So you have this one. This one, John. So let's say this is the graph G that we have. and this is the graph H that we have. Okay, so this is H. Okay, now we have the same number of vertices, 8, both sides. We have the same number of edges, there are 10 edges, right? And the degree are also matching. Okay, if you look at it, you have, so this is degree 2, this is degree 2, this is degree 2, this is degree 2. Is it okay? And then this is 3, 3, 3, 3. These are the degrees. And here, this is 2, 2, 2, 2. And this is 3, 3, 3, 3. Is that okay? So you have, is that okay? You have degree, they're having exactly 4 degree 2 vertices in each side and exactly 4 degree 3 vertices in each side. Okay, so can we still, okay, so we have talked about degree. How about, do we have any graph properties that we can talk about? So, any idea? So what kind of graph properties? So apart from degree, so we have vertices, numbers, we have edge numbers, we have degrees. Okay. Yes. Subgraph. Okay, good. Okay, good. Okay, so how do you look at subgraph? Let's see. Subgraph. Yes. Yes, we can talk about subgraph. Or, okay, I elaborate with him. So there are many kinds of subgraph we can talk about. In particular, we have also mentioned one kind of subgraph. There's path. So path is a certain kind of a subgraph, right? So it is a sequence of vertices so that you have edge joining each other. Look at this. So you have degree 2 vertices, and then there is a direct edge between 2 degree 2 vertices. Am I correct? And here, you don't. For any degree 2 vertex, the neighbor is not degree 2. So here, for this one, for any degree 2 vertex, there is a neighbor of degree 2. You don't have every degree 2 vertex. You just need to show that there exists a degree 2 vertex such that it has a neighbor which is also a degree 2 vertex. Is that okay? Is that okay? So in that sense, these two cannot be the same. If they are the same, then the degree 2 vertices of this side must be mapped to the degree 2 vertices on that side. Am I correct? If there is no neighboring degree 2 vertices, then we should not have neighboring degree 2 vertices here. But then it is impossible. Okay, so if you look at it, you have degree 2 here. You don't have degree 2 joining degree 2. So this is another case. Is that okay? Now, so usually there is no rule about, or we have actually one more. We can also talk about whether a graph is two-colorable, whether it is bipartite or not. Let's see if it can help us. Okay. So is this graph bipartite? Let's try. Okay, so this is vertex, right? So you have white. So this is black. So this is black. So this is black. Is that okay? Well, bipartite doesn't help us. So this is, we can still do this. Okay. Okay. Well, this doesn't help a lot. This doesn't help a lot. But then, it's okay. So again, we will need. Okay, bipartite does not help us directly. So both graphs actually are bipartite. So originally, I hope to find that okay, this side is bipartite, this side is not. Then in that case, they cannot be isomorphic, right? But unfortunately, this side is bipartite. This side is also bipartite. But again, although they are bipartite, there is, are there 3, 3, 2, well, no. Okay, in that case, we don't have a very easy argument here. So that means what? That means to check whether two graphs are not isomorphic, if we are lucky, then we get a very simple argument. If we are not, then yeah, try our best. Okay, so this kind of so hopefully in the exam or in the exam we'll give you something that we hope that there is a very short proof. I don't know. We haven't designed the question yet, but this is what we want. Okay. Okay, so these are there is one more concept I want to talk about. Okay. So this is one final easy concept. We call it complements of a graph. So the idea is very simple. You have a graph, let's say this is called G, let's say on a couple of vertices. So let's say this is a graph G. Okay. Then we can define the complement of graph G to be based on the same set of vertices. So we have this vertex labeled A, B, C, D, E. So it has this notation. So it is based on the same set of vertices such that, so A, B, C, D, E, okay, such that there is an edge here if and only if there is not an edge here. So we have the edge to be in complement. So there is an edge AE, we don't draw it. There is an edge DE, we don't draw it. But there is no edge EC, we draw it. There is no edge EB, we draw it. There is no edge BC, we draw it. There is no edge AB, we draw it. Is that okay? So this is called the complement of this graph. Is that okay? Okay. Okay, now let me give you an IQ question. Okay. Can you give, so let's say G, so design a graph G such that the number of vertices in G is equal to 5. So there are 5 vertices in G, and G and its complements are isomorphic. So isomorphic, let's define a notation for it. Maybe this one. So they look similar and the same to each other. Do you understand my question? Find a graph that has 5 vertices such that what? Such that the graph itself and the complement are isomorphic. How many edges are there? So first of all, how many edges in each of these graphs? Okay, 10 will be the total number of edges in the complete graph. Is that okay? Now, if you want a graph and its complement to be isomorphic, then each of them must have 5 edges. Is that okay? Good. Is there an easy way to show? Good. Okay. So the answer is, so it may not be the unique answer, but this is the answer that I find it easiest to remember. You have this one, and you have this one. Is that okay? Both of them is a path that can start from one vertex going back to itself. So both of them is a cycle. This is a C5. This is also a C5. Is that okay? Is that okay? How about, if you're okay with this, could you please raise your hand? Okay, excellent. How about 4? How about 4? So can we find a graph that has 4 vertices, and then the graph is isomorphic to the complement of itself? Well, you can do this by trial and error, and it's not that difficult to find. So this is one way. Okay. And the other way is this one. Is that okay? Is that okay? So both of them is a path of length 3 edges. Is that okay? If you're okay with this, could you please raise your hand? Excellent. Okay, how about 6? Can we find a graph with 6 vertices such that the graph itself and the complements will be isomorphic to each other? No. Someone says no. If you think there's no way, could you please raise your hand? Okay, excellent. Why? Why there's no way? Why? Why? Edge. Very good. How many edges are there? For a complete graph, so the graph G together with the complement of G combined will give us a complete graph with 6 vertices. Is that okay? And in this complete graph, how many edges are there? There are going to be 6 choose 2 edges, 15 edges. And it is impossible to make G and G complement to have the same number of edges. And so G and G complements can never be isomorphic. Is that okay? Okay, good, very good. So this is about the final concept of a graph. Okay. Now, okay, so the next topic we are going to talk about is a problem called Euler path problem or Euler circuit problem. So I hope you still recall. So let's get a graph. So this is A, B, C, D, E. So let's have a. So what is a path? A path is so let's first define a path. A path is a sequence of vertices such that between adjacent pair there is an edge. So A, B, C, E. So this sequence A, B, C, E is a path. Is that okay? And A, B, A is also a path. Because by definition, A, B, A, it is like I walk here to this one and go back. Okay. Okay. And you can have A, B, C, E, C, B, C, E, D, C, D, E, C. This is also a path. Is that okay? So as long as when you make adjacent move, then there is an edge joining the start and end vertices of that move. Is that okay? So you can have a path. But some paths, you don't repeat the vertices. We will call it a simple path. Okay? And some paths, in general, you may repeat the vertices. We call it a general path. Is that okay? There is a special kind of a path that goes back to itself. So if you start at E, C, D, E, it goes back to itself. E, C, D, E. It goes back to itself. Then it is called a circuit. Circuit. It is called a circuit. Okay, so ABA is also a circuit. And then we can talk about a simple circuit. Okay, so now what is Euler path and what is Euler circuit? We are going to define 2 new concepts. So you have a graph. Let's say it looks like this. Okay, let's say you have A, B, C, D, E. Okay, an Euler path on a graph is a path that visits each edge exactly once. Okay, so Euler path on a graph G is a path that visits each edge exactly once. So this is important. So each edge has to be visited, and then each edge can only be visited one time. So let's see. So suppose that this is the graph that we have. So we have A, B, C, D, E. Okay, if this is the case, then in Chinese we can call it Yi, Bi, Hua, Hua. Okay, okay. So we call this like this. So let's check if this is a Yi, Bi, Hua or has an Euler path. So let's try A to E, and then go to this one, 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 and go to this one. Is that okay? Okay. So this is a graph that has an Euler path. But some graph you may not have an Euler path. You can simply look at this. This is a very simple graph, and you can't have any Euler path. If you start at this vertex, you go here and you go here, and then you cannot visit this one, because we cannot come back. Each edge can only be visited exactly once. Okay, so there is a problem to check if a graph has an Euler path or not. Okay, and moreover, if you start at a certain vertex and you draw the Euler path and you end at the same vertex, then it is called an Euler circuit. Is that okay? Good.